BC Calculus, Lesson 5.4, Modeling and Optimization. There's a lot of computation in this, so be prepared to pause the video if you need. I'm going to blow through things. We're going back and forth between theory and application, so we're back to application. And one of the biggest applications is what we call min-max problems. So we look at this question. It says find two numbers sum to 20. So x plus y equals 20. And they have the biggest possible product. So x times y equals max. So what we got to do is get everything in one variable. So I'm going to make this y equals 20 minus x. And then we say the function we're trying to max out is x times 20 minus x, which is negative x squared plus 20x. So then we take the derivative, because that's going to find us maxes and mins. Negative 2x plus 20, and we set it equal to 0. After all is said and done, we'll say x equals 10. And then the other number, x equals 10, therefore y has to equal 10. Now, we have to be careful with this because we have to make sure we just found a max, not a min. But if I look at the function here, I know it's going to graph, and this is well, I'll try and do it somewhat correctly. I was going to say it's incorrect. It's going to graph like that. This would be a max at a 10 over here. And I believe that'll get us 100 if I'm not mistaken. Negative 100 plus 200 is 100. So that's the max. So when you do these, make sure you know what you're talking about. That's all I have to say about that. How can we rewrite this as a rectangle problem? Because we're going to do a lot of geometry problems that you have to mess with. And we could say the perimeter equals 40. What's the max area we can get? So we would say, okay, we got this rectangle, x, y, x, y. And then we would write 2x plus 2y equals 40, which is the same as x plus y equals 20. And now we're back where we started up here. So that's just an example of how this could actually be a geometry one. Here's another one. A rectangle is inscribed under an arch of a sine curve. So it's just the first one. So this is pi, and here's the rectangle. So we'll make this to here some hypothetical x, which means that this point is x comma sine of x. Since it's sine, we know this would also be x. And this distance here has to be pi minus 2x. Doing this very, very quickly, I apologize. Therefore, the area equals sine of x times pi minus 2x. The derivative equals, yeah, I think I'll just leave it as is. I multiplied it out last time, but I'm not going to this time. Leave it alone, take the derivative, leave it alone. So we have we're going to set this equal to 0. And a lot of people say, well, how do you factor that or solve it or do what? And I say, I'm not going to. I'm going to put this in the calculator just like it is and find my roots. And if you look carefully, you'll find two roots. One at 0.710. And then there's one bigger than that, but you can't go bigger than that. A lot of people say, well, I got one over here. So then your square is going to bounce back. So you're really kind of stuck with this whole domain between 0 and pi over 2. And this is what we mean by be intelligent about looking at the problem. Think about it before you just kind of slap some information together. Now, also read the question because now we have to find the area. And we would plug it in here and here. And again, I'm just not in the mood to do all the computation, so the area is 1.122 units squared. And this is 0.710 units. So there it is. Now, any advice? Draw a picture. Always, 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 always. What are you looking for? Because a lot of people are like, well, why'd you do this? I said, well, what are we looking for? And they say, oh, that's what we're looking for, so we have to actually find something. And then at the end, check if you found a min or a max. You can get off track very readily if you're not careful. So here's an example. You can read it. It's basically saying there's a box. We're cutting out of a square piece of tin foil. Extremely challenging to draw. And this is 25 inches. This is 20 inches. And each of these corners are X because they're going to be square. And we're going to fold this box up on these dotted lines to make the box. And then we'll weld the corners or whatever. So we want to max out the volume. So we find a volume formula. X times 25 minus 2x times 20 minus 2x. Volume of x is 4x to the third minus 90x squared plus 500x. The derivative is 12x squared minus 180x plus 500, and the roots are 3.681 inches and 11.317, which we cross out. If you think about, there's two x's, one here and one here, you definitely can't fit 11.317 in there. Then we plug it back in to find the volume, 3.681. We say the total volume is about 820.528. And that, of course, is plugging 3.681 in there. So that's how big you want to make the box. And I've actually done a little of this in the real world. And yeah, the calculus comes in handy. There's way, way, way more real life problems. How big, how much packing, how much cushion, how's it's going to be shipped that you have to really worry about. But so another one, we've got a 1 liter can, which we're going to call 1,000 cubic centimeters. And that's pi r squared h. And then we've got the surface area that we want to minimize, which is 2 pi r h plus 2 pi r squared. That's the outer piece, and then that's the two ends. So we're going to solve this one up here because we want to minimize the surface area. For h, we'll get h equals 1,000 over pi r squared. And then we say surface area equals 2 pi r times 1,000 over pi r squared plus 2 pi r squared. So we're going to find the radius first. Derivative of surface area with respect to r. And I'm going to do my best to cut to the chase because I'm going to be really low on time. Should get you to 4 pi r. Notice I didn't even finish simplifying that, which I should have. Minus 2,000 over r squared. Set it equal to 0. And you will find r equals about 5.419 centimeters. So think about it, graph it, make sure that's a max or min in this case. No, hang on, I gotta think about this. I want to minimize the surface area, so that's a min. Graph it, make sure that's the case. Then plug it back in. H equals 1,000 1000 over pi 5.419 squared, and h equals, yeah, they take second derivative, check that out, 2 times that, which is 10.839 centimeter. And off we go. Pulling through all that quick, I would make sure the calculus works out for you. I'm fairly confident it's correct. A lot of examples of this in economics, the biggest of which is that the marginal revenue, which is the derivative of the revenue, and the marginal cost, which is the derivative of the cost, should be set equal to get your maximum profit. I'm not going to go into why that is because it's complicated, but it's definitely going to happen at that point. If you can keep making money, if your money you get in is more than the money you're sending out, keep making it. The second you realize, whoa, my cost and my revenue are about the same, that's when you stop. So r prime of x equals 9, c prime of x equals 3x squared minus 12x plus 15. Set them equal. Solve with a calculator, quadratic formula, and you get x equals 0.586. Or 3.414. So I'm actually going to say this is the function I was messing with. And then that's the derivative. Second derivative would be 6x minus 12. And at 0.586, that's negative. And at 3.414, that's positive. So this is a maximum loss here, and you would have to play with this to understand why. And this is where we actually want to manufacture. You'd have to go back and say, what's my profit? And you know what? Forget the second derivative. Shouldn't have even brought it up. Just plug it back into here and see which one's going to max it out. Turns out you want x equals 3,414. Yeah, because these are in thousands. Units. Yeah, definitely play with this. Make sure you know what's going on. Production, we want the average cost as smallest. It's where the average cost equals the marginal cost. That's a tricky concept. So marginal cost is c prime of x, 3x squared minus 12x plus 15. Average cost equals x to the third minus 6x squared plus 15x over however many we sold. And set them equal. Oh, well, this is x squared minus 6x plus 15. So 3x squared minus 12x plus 15 equals x squared minus 6x plus 15. 2x squared minus 6x equals 0. X equals 0 or 3. X has to be greater than 0. We have to actually make something, so we'll cross that one out. And it turns out we want to produce at 3 if we're looking for an average cost that's minimum. It would really help if we had a lot more specifics about this, but Again, just giving you a quick one to run with. So is it realistic to say these functions are continuous? Not really. They're discrete, meaning whole values. We can't produce 0.5 cans of Pepsi. But the numbers are big enough that we can treat it as continuous. So you do not need to worry about it. But we've spent a lot of time making sure our theory is really, really tight, so it's a legitimate question. That was quick. Good luck and happy mathing.